Hello, good morning to all of you. After the Hartree-Fock method, which actually do not includes any electron correlations, we are now discussing about the electron correlation method. So in last two lectures, we have discussed about the electron correlations and the correlation energy. The type of correlation means dynamic or static correlations, and the perturbation theorem, molar placid perturbation theory, which includes the electron correlations. And also we have discussed about the CI, that is configuration interaction method. So in this lecture also we are going to discuss few more sophisticated methods which actually incorporates more accurately the electron correlations and provides the energy more accurately also. But again, these methods are extremely expensive because it takes too much time to calculate. So for this reason, we cannot use for all the systems. But if we can able to use this, then we will definitely get much better energy corresponding to with respect to other normal Hartree-Fock method. So here one new method is the multi-configurational self-consistent field. So this is also same like a CI. It's use multiple determinant, but the orbitals are here optimized for use with the multiple determinant wave function. Okay. So compared to CI calculation, and MCSCF means this multi-configuration self-consistent field gives more of the correlation energy with fewer configurations. However, if we consider total correlation energy, then CI will provide more, because in CI many more configurations are included with respect greater than the MCSCF. So these methods are actually requires more technical sophistication, because on the part of the user, this is because that there is no completely automated way to choose the which configuration should we use. Okay, that is which configurations will be active in our calculations. So basically, the user must have to determine that which molecular orbital to use in these calculations. So in choosing which orbitals to include, the user should ensure that the bonding and the corresponding antibonding orbitals must be included, because you know again, the chemistry is the bond breaking and bond making process, and during the chemical reactions, whatever the changes takes place, it happens in the bonding or antibonding electrons and their orbitals. Okay, so basically we must have to include these bonding and antibonding orbitals in our active space in the multi-configurational self-consistent field calculations. So there are two types of multi-configuration self-consistent field. If we include the all combinations of active space orbitals, which included it's called complete active space self-consistent field, that is CAS SCF. And also there are one type of calculations, like if we only consider two configuration SCF, then it is TC-SCF. So another more sophisticated method is multi-reference configuration interactions. You know the CI earlier. Now you are reading the MRCI. So MRCI is different than the CI is in one respect, that in CI our reference state was the Hartree-Fock determinant. If you can remember the image that we have started from the Hartree-Fock determinant for CI calculations. But here we will use the multi-reference configuration interactions as the reference. Okay. So we actually MRCI actually takes the reference state is the multi-configuration SCF calculations. Okay. So the starting wave function is called the reference state. For CI it is the Hartree-Fock wave function, but in case of MRCI it is MCSCF wave function. So there are configuration interaction determinants in this type of calculations than in conventional CI. So more and more configuration interaction determinants are actually available in these calculations. So this type of calculations can also be extremely time consuming, but can give you an optimal amount of correlations for some problems. Next one is the coupled cluster, which is the most powerful method in quantum chemistry. You can say this is called one of the gold standard method. So coupled cluster calculations are also similar to configuration interactions calculations, but in that case the wave function is linear combinations of many determinants. So we first actually take many determinants wave functions and then we are actually make them a linear combinations. However, the means for choosing the determinants in a coupled cluster calculation is more complex than the choice of determinants in CI. So this is more tough to choose. So like CI, there are also various order of the coupled cluster expansion, like CCST means coupled clusters single and double excitation included. CCSDT means the coupled clusters single and double and triple excitations are included, and you are getting more and more accurate energy. So a calculations denoted by CCSD and T in the bracket is one in which the triple excitation are included perturbatively rather than exactly. So all these methods are actually incorporated in the quantum chemistry programs which we will use for our calculations. So we can see that how we can improve the calculations or getting a more accurate energy using these sophisticated methods. So now before the end of this lecture, we will discuss a little bit about the strength and weakness of the ab initio calculations, which we have started from the Hartree-Fock, and we are going to end it after incorporating the so many methods for the correlations. So ab initio calculations are based on a fundamental physical equations, you know, that is the Schrodinger equations, without any type of empirical adjustments. So this ensures that they will give correct answers provided approximations needed to solve the Schrodinger equations. Okay. Ab initio calculations can be performed for many kind of molecular species, including transition state and non-stationary points also, because it can explain the reactivity, it can explain the reactions, it can explain the transition state, because it considers the electrons explicitly. So all the bond breaking, bond making phenomena will be able to explain here. And also one more important point here, that the accuracy of the calculations can be improved by reducing the degree of approximations. Means that Hartree-Fock, which has taken a very high degree of approximation, provides crude results. But if we want to move HF to CCSDT, then what we are doing, we are actually reducing the approximation degree of approximations, and we will able to get the more and more accurate results. Okay. So another way we can also incorporate that, we also increase the number of basis functions to get the better results. Okay. So these characteristics of reliability and generality are the strength of ab initio calculations. Okay. And weakness, the main and important weakness of these ab initio calculations are they are extremely demanding, they are slow, they are relatively they are not feasible for the systems, maybe more than 100 atoms, or maybe more than less than that also. Okay, for CCSDT, the calculations for 5-6 atoms also take so many days. Okay, in current resources. So the problem can be solved. This slow problem, which actually commercial demanding, this problem can be solved by increasing the speed of computer hardware, means the processor or memory, using more efficient algorithm or software. Okay. So now let's make a summary of the ab initio methods. So ab initio calculations actually based on the solving the Schrodinger equations. Basically, it's the approximate Schrodinger equation calculations, and the simplest approach is the Hartree-Fock method, where the total wave function psi is expressed is a single Slater determinant, and the molecular energy is actually computed using the expectation value of the wave function, that is psi star psi h psi d tau, if psi is the normalized function. So the special orbitals are approximated as a linear combinations of basis function, that is we say the basis set, and these are actually identified with atomic orbitals, but sometimes also any type of mathematical wave functions can be taken, that is the wave function which gives reasonable answer where you do the calculations. Okay, and the last slide of this we can discuss that there are many problems also in all the method. Like for Hartree-Fock method, the main problem is that it does not treat electron correlation properly. Each electron is considered here to move an electrostatic field represented by the average cloud of the other electrons, whereas actually electrons avoid each other better than this model picture. Okay, so electron correlation is treated better in post-Hartree-Fock methods such as molar placed perturbation theory, configuration interactions, configuration interaction method, couple cluster method, etc. And the main use of the ab initio method are calculating molecular geometry. It can calculate energies, more accurately vibrational frequencies, spectra of any types, because it's considered the electronic pattern, electronic distribution, electron transition. So you can get the data of the spectra, ionization energies, reaction mechanism, electron affinity, and the dipole moment. All the things which are directly related to the electron distributions, everything you can calculate using the ab initio methods. Okay, so thank you very much.